Pluto, a previous planet that was downsized to a Bantam planet, stays a subject of interest and concentration in the cosmic local area as shown by later figures by driving analysts. Pluto's circle is dangerously near Neptune's. Astrophysicist Neil deGrasse Tyson and Mayo Kaku are both raising the alert about a possibly perilous impact between these two planets, which could represent a basic gamble to Earth. Yet how is such an occasion even conceivable? Pluto's excursion around the Sun isn't like any other planet in our planetary group. It requires a stunning 248 years to finish a solitary circle, meaning that since its discovery in 1930 it hasn't even completed one full revolution. Yet the interest doesn't stop there. Pluto's circle is set apart by its astoundingly bended shape, meandering out and away from the near-round circles of the major planets. What makes Pluto's circle even more intriguing is its slant set at 17 degrees to the ecliptic plane. The way Pluto follows its circle is essentially more outrageous compared to different planets. This tendency and flightiness add layers of intricacy to its orbital plan. Perhaps one of the most intriguing parts of Pluto's circle is its convergence point with Neptune's circle. For around 20 years in each circle, Pluto actually draws nearer to the Sun than Neptune, standing in contrast to what we might expect based on their positions in the solar system. This prompts the regular inquiry: why hasn't Pluto slammed into Neptune? The response lies in the gravitational impacts of different planets. The investigation of Pluto's circle began not long after its discovery. Initially, stargazers attempted to sort out its abnormal way, not at all like other planets whose circles lie for the most part close to the ecliptic plane. Pluto's circle juts with its lofty tendency and length and shape. The secret grew with the acknowledgement that Pluto's circle does for sure cross Neptune's. The strength of Pluto's circle in the midst of these intricacies is proof of the unpredictable mechanics of space. The three-body issue in space involves sorting out how three items like Pluto, Neptune, and the Sun move and cooperate with one another due to their gravity. It's like attempting to foresee where they will go in light of where they begin and how the manner in which they pull on each other works for Pluto's situation. This issue shows how its circle, Neptune's circle, and the Sun's gravity all work together in a complex way. The terms alpha libration and degree rel libration alongside the VZK swaying are critical to addressing this puzzle. As shown by astrophysicists, what keeps all planets in their circles is a peculiarity called alpha libration. In the instance of Pluto and Neptune, this term implies that at whatever point Pluto crosses Neptune's circle, it is no less than 90 degrees away from Neptune. This spatial partition is basic in keeping their circles from crossing. Extension libration, on the other hand, alludes to the vertical development of a body in its circle. For Pluto, this implies that when it comes nearest to Neptune or some other giant planet, it is situated well above their orbital plane, giving an additional layer of insurance from potential impacts. Another critical thought is the VZK sway, named after three analysts, Bon, Zippel, Leo, and Kai, who concentrated on how objects move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational force influences how they move. In Pluto's case, the VZK helps explain why its circle around the Sun is so strange despite its seemingly inconsistent way. This swaying helps keep Pluto moving flawlessly for billions of years. The VZK wavering shows that, despite the fact that things in space may seem tumultuous and irregular, some examples and for keep everything together, these elements help maintain Pluto's circle, ensuring it doesn't crash into Neptune or get lost. This three-body issue is significant for grasping how circles change because of how space objects pull on each other. Concentrating on this helps us dive deeper into Pluto, our solar system, and far-off stars and planets. Numerical reenactments in the late 1980s uncovered that regardless of these balancing out properties, Pluto's circle is in fact tumultuous with slight deviations in starting circumstances, leading to huge changes over the long haul. Anyway, these weird properties of Pluto's circle have been found to mainly maintain stability over incredibly prolonged timescales, keeping the mayhem under tight restraints. Late PC models have assisted us with grasping how giant planets like Neptune, Jupiter, and Saturn impact Pluto's way around the Sun. Neptune has a unique relationship with Pluto, where for every 2 circles Pluto finishes around the Sun, Neptune finishes 3. This reverberation settles Pluto's circle, but Neptune isn't the only component. Jupiter's gravity likewise plays a tremendous part in protecting Pluto's circle, and Saturn contributes as well. These investigations show that Jupiter's gravity alone is sufficiently strong to ensure Pluto stays on a steady way for an extended period, possibly even billions of years. So it's like Neptune, Jupiter, and Saturn are cooperating to ensure Pluto continues moving safely in space without getting into trouble. These characteristics are crucial in the larger context of the universe, keeping everything together and maintaining safety in the movement of celestial bodies. Without these parts, the nearby planet group as we probably know it would be a considerably more chaotic place, with bodies like Pluto perhaps crashing into others or being flung out of their stable circles, leading to a cascading impact on other divine objects. For Pluto, especially in conversations about its potential contact with Neptune in the future, understanding its circle is essential. This gives us a clearer picture of the solar system's dynamic nature. The instance of Pluto shows how even the most apparently unsound of circles can come to a condition of equilibrium through the multifaceted interchange of gravitational forces and orbital mechanics. It also highlights the importance of continued observation and investigation of these characteristics to better understand our place in the universe. Investigating the depths of space frequently leads us to face the weird nature of heavenly bodies, and Pluto's circle is an ideal illustration of this peculiarity. The idea of orbital chaos, which alludes to the sensitive reliance of a body's path on its underlying circumstances, is clearly shown in Pluto's case. This implies that even slight changes in Pluto's position or speed can decisively adjust its long-term direction within the vast area of our solar system. Pluto occupies a unique place that challenges how we might interpret planetary classification and elements. Since its discovery in 1930, Pluto has gone through extensive review, leading to significant discoveries about its creation and conduct. Quite possibly one of the most charming parts of Pluto is its surface, which is a complicated embroidery of ice rock and various Mixtures. The New Horizons mission, which flew by Pluto in July 2015, provided amazing information about this far-off world. Pluto's surface is described by immense fields transcending mountains and deep valleys. One of the most striking features is Sputnik Planitia, a monstrous heart-shaped plain primarily made of nitrogen ice. This area exhibits a diverse array of topographical features, including huge ice blocks and what appear to be flowing ice sheets. The presence of these features suggests that Pluto might still be topographically active despite its significant distance from the Sun and low temperatures. Another intriguing part of Pluto is its atmosphere, which is primarily made of nitrogen with hints of methane and carbon monoxide. Pluto's atmosphere is thin but shows charming seasonal variations as Pluto moves closer to the Sun. In its extended circle, its atmosphere can expand and become more powerful. This behavior mirrors the intricate relationship between Pluto and its air during Pluto's closest approach to the Sun. Some of the atmospheric gases might freeze out onto the surface, while as it moves farther away these gases can sublimate back into the atmosphere. The relationship between Pluto and its largest moon, Charon, moreover adds intricacy to the system. Charon is somewhat large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies orbit a point in space that lies between them, as opposed to Pluto simply orbiting Charon. This unique relationship adds to the gravitational dynamics of the area, impacting the orbits of other objects in the Kuiper belt. The Kuiper belt, an area beyond Neptune populated by small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a repository of ancient material from the early solar system, offering researchers a brief look into its evolution. Pluto's orbital attributes might give insights into the development patterns of these far-off objects, suggesting collaborations with larger planets may have played a critical role in shaping their current orbits. One of the key implications of understanding Pluto's orbital components is its potential impact on how we might interpret the solar system's development. Gravitational effects from neighboring giant planets like Jupiter and Neptune can modify the orbits of smaller bodies, including those in the Kuiper belt. Such interactions can lead to changes in orbits, possibly causing crashes or ejection from the solar system. As researchers continue to consider these connections, they might reveal broader patterns that govern the behavior of celestial bodies across the universe. The investigation of Pluto also raises philosophical inquiries about order in cosmology. The decision to rename Pluto as a dwarf planet in 2006 sparked debates about what defines a planet. The International Astronomical Union's definition focused on criteria like orbital dominance and size, leaving many to consider the implications of such classifications. This ongoing conversation reflects our growing understanding of the universe and highlights the need for a flexible approach to classifying celestial bodies. Moreover, the potential for future exploration of Pluto and the Kuiper belt remains an exciting frontier. With advances in technology and mission planning, researchers are considering sending additional spacecraft to study Pluto as well as other objects with similar orbital characteristics. Such missions could provide valuable data about the primordial materials that formed our solar system, possibly shedding light on the origins of life on Earth. The role of exoplanets. Planets beyond our solar system is another enthralling area of study that intersects with our understanding of Pluto as astronomers discover an increasing number of exoplanets, especially those in the habitable zones of their stars. The lessons learned from studying our own solar system might help develop hypotheses about planetary formation and habitability. Ultimately, public interest in Pluto has remained strong due to its strange status and the stunning images returned by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, inspiring a renewed appreciation for the vastness of space and our place within it as we continue to unravel the mysteries of Pluto and the celestial bodies at the edge of the universe. We are reminded of the wonder-inducing marvels the universe has to offer. Does Pluto's amazing nature extend beyond its physical properties and orbit? It also serves as an essential case study for understanding planetary development and the dynamics of celestial bodies. Pluto's formation is believed to have occurred in the early solar system alongside other Kuiper belt objects. Studying its composition can offer insights into the conditions that prevailed during the formative stages of the solar system, possibly revealing clues about the development of Earth-like planets. Later exploration suggests that Pluto might have a subsurface ocean, a discovery that could alter how we understand its geology and possibly support life. New Horizons data revealed that some regions of Pluto's surface, such as the icy mountains, may be made of water ice which behaves differently from typical rock at low temperatures. This discovery invites further exploration into the possibility of liquid water existing beneath its frozen outer layer, raising intriguing questions about the potential for life indeed even in such extreme conditions. Also, Pluto's relationship with its atmosphere can offer insights into atmospheric science. The seasonal changes in its thin atmosphere provide a natural laboratory for studying climatic cycles. On a planetary scale, scientists are especially interested in how the relationship between solar radiation and the surface can lead to complex weather patterns similar to those observed on larger planets.